I think we'll go ahead and get started. My name is David Granger. I'm the chair of the Department of OBGYN at the University of Kansas School of Medicine in Wichita. And we want to welcome everyone who is joining us this morning for an incredibly exciting lecture series by a very well-known individual. This speakership is part of a Bohan Speaker Award from the University of Kansas. And I have to tell you that I enjoyed reading the committee's comments on the selection of this speaker. It was very encouraging that this speaker would be well received in our community here in Kansas. Dr. Adachi is well known, is an understatement, in the area of reproductive medicine. He is a graduate of Tel Aviv University. He did his residency at Tufts University, reproductive endocrinology at Johns Hopkins and USCD. And for his faculty appointments, went from Maryland for a few years to Utah for a few years to where he is now residing at Brown University. He has been the Dean of Medicine and Biological Sciences at Brown University and is a professor emeritus at that university. He has been funded all of his life, I think, has numerous publications, book chapters, has served as a mentor for many students, and has almost 600 peer-reviewed publications. He has connections to Wichita through the Women's Research Institute from very early on. It is truly a pleasure to welcome him today to speak to us. His first lecture is on eggs and sperm from a buccal smear, and that will be this lecture. And at 9:30, he will lecture on remedial germline editing prospects and possibilities. So I would like to welcome you, Ellie, as a colleague and a friend, and the floor is yours.
Thank you so much, David. I assume you can hear me, is that correct?
Yes.
And thank you so much.
We can hear you. We can hear you fine.
Thank you so much. And it's wonderful to quote unquote see you, if you will. It's been a while. As you noted, during the 80s and the 90s, I used to visit with some frequency in connection with the Research Institute. But since then, it's been less frequent, although I seem to recall a visit now approximately a decade ago for grand rounds, on which occasion I remember very pleasant memories from seeing yourself, Dr. Roberts, the dean of the medical school at the time. And so I'm obviously delighted to renew the connection after all this time with COVID as a background, which is the reason why I'm not there in person. Today, we will be speaking about the future. And when I say future, not really all that distant a future, but an exciting and amazing future that could not have been foreseen only a few years ago. The subject matter today is really the application of embryonic or induced stem cells, in this case for reproductive purposes, although it is important to note that our field of reproduction is hardly the sole beneficiary of either embryonic or induced pluripotent stem cells. There are other disciplines who are exploring possibilities such as creating amacrine neurons for the retina in certain cases of blindness, dopaminergic neurons for the striatum, for example, in the context of Parkinson's disease, or motor neurons for individuals who are paralyzed and who, in principle, could be cured if and when this technology is perfected. But we are going to limit ourselves today to stem cell-derived gametes. And to just give you a sense of how society at large is beginning to appreciate this as an evolving reality, here's a full spread from Science magazine from 2021, a review that was dedicated to mammalian in vitro gametogenesis by the leaders of the field, to whom I'll come back, of course, in the course of our presentation. The New England Journal of Medicine came to the same conclusion, and last year it published a review on oocytes from stem cells. So as you can see, this is no longer a fringe phenomenon. This is becoming very much an accepted reality that the leading journals have realized and have therefore dedicated page space to them. I should also note that actually next week, next Wednesday, the National Academy of Medicine will have a workshop that will be dedicated to in vitro gametogenesis. It's a 2.5-day affair, which I happen to chair, and it will feature a long list of speakers from all over the world, many of whom will participate via Zoom, but that will give anybody who wishes to register, and it's free, of course, really a complete view of where this field stands today, to a degree that is probably not possible in a presentation like mine this morning. And so those of you who are interested, please either let me know or go on the National Academy of Medicine website and register. Registration is free. To begin our conversation today, I chose to display a slide, or an infographic, if you will, that is annually issued by the Nuffield Council on Bioethics, which, as you may know, is the prime bioethics organization of the United Kingdom. Each year they produce this infographic, which serves their purpose of informing us what they're likely to tackle in the coming year. So, for example, in human reproduction, they propose to tackle in vitro derived gametes. In fact, it's notable that this is at the very top of their list. They will also tackle time limits on maintaining embryos in culture, womb replacement, preconception screening, whole genome sequencing of embryos and fetuses, genome editing of gametes and embryos, and egg freezing. And then, of course, they go to other arenas of human endeavor. But in human reproduction, those are the topics they plan to address. And as you can see, in vitro gametogenesis is leading the pack. I think we can all agree that in vitro gametogenesis is a disruptive technology. Whether or not it's achievable in the human, of course, will become apparent in the next few years. And I suspect, as I alluded to earlier, that the timeline is short. By that I mean a decade, two, we'll have to see. All of which brings us back to the well-known book of Aldous Huxley from 1932, which was titled Brave New World, wherein he projected on the future of reproduction. In a way, that's what we're doing today. And it's interesting to go back to some of Huxley's predictions, which included that eggs will be produced via ex vivo ovarian cultures, not exactly in vitro gametogenesis, but close. He also predicted that embryos will be produced via in vitro fertilization, and of course, he got that perfectly right. And he suggested that newborns will be born via ex vivo ectogenesis, that is to say, babies will no longer be carried by their mothers, but rather by an artificial womb, which has yet to be realized. But of course, he was spot on by predicting IVF, which has been with us now since 1978. And he predicted this long before. His view of how eggs will be produced is explicated here. In chapter 1 of Brave New World, the director of the hatcheries, so-called, and conditioning, said, quote, "One egg, one embryo, one adult, normality. Making 96 human beings grow where only one grew before, progress." So he clearly could foresee mass production of gametes, in this case, eggs. And in that respect, he was again very close to the truth, because today, as you will see, we are approaching the point wherein we will be growing essentially limitless numbers of eggs or sperm in 96 well plates like this one, which effectively is what Huxley foresaw at his time. It's not clear that there'll be limits on scale or on choice. And of course, there's always the challenging question of disposition of embryos, because when you move to a scale such as this, the issues we are now encountering in this arena are going to be multiplied manifold. But before we go there, it's important to review briefly the history of this field. And one has to go back to what was known as the soma-germline barrier hypothesis, which effectively argued that you could never produce gametes from somatic tissues, which is exactly what we're doing today. But for the longest of time, thanks to Professor Weissman, professor of zoology at the University of Freiburg, who came up with a theory that, known as the germ plasm, a theory of heredity, according to which there really could not be physically possible to convert a somatic cell to a germ cell. In his view, the germline correctly gives rise to the soma, which is immortal, that is to say, the germline. The soma, on the other hand, never gives rise to the germline, was his view, which is mortal, but which we, of course, at this point can say, in hindsight, was incorrect. Namely, courtesy of pluripotent stem cells, we can, in fact, take a somatic cell and produce a germ cell. So we are talking about taking a differentiated somatic cell, say a skin cell, converting it to a pluripotent stem cell by means that I will describe, and then guiding that pluripotent stem cell towards a gametogenic fate. The first type of pluripotent stem cells are known as embryonic pluripotent stem cells. And they're produced by a technology known as somatic cell nuclear transfer, or SCNT for short. This dates back to 1958, when John Garden, a British scientist from Cambridge University, published a leading article in Nature titled "Sexually Mature Individuals of Xenopus laevis from the Transplantation of Single Somatic Nuclei." Essentially, he began with a somatic karyoplast, that is to say, a nucleus. He injected it into an oocytic cytoplast, that is to say, an oocyte that was lacking a nucleus, and created a quasi-zygote that proceeded to develop into a blastocyst, the inner cell mass of which could then be harvested to produce embryonic stem cells. The second type of pluripotent stem cells are known as induced pluripotent stem cells, and that discovery dates back to 2006 and is attributable to Professor Shinya Yamanaka from Kyoto University, who published a seminal paper in Cell titled "Induction of Pluripotent Stem Cells from Mouse Embryonic and Adult Fibroblast Cultures by Defined Factors." His approach, also starting with the somatic cell, was to transfect that somatic cells with a select group of transcription factors which he identified, which were able to convert that somatic cell into an induced pluripotent stem cells. So now we have two different technologies which lead to the same common outcome. For these discoveries, Professors Yamanaka and Garden received the Nobel Prize in Physiology and Medicine in 2012. So in vitro gametogenesis, going back to our field, entails a starting material, which is the somatic cell. And then you could apply a technology that would convert it either to an embryonic or induced pluripotent stem cell, and then guide that pluripotent stem cell towards a gametogenic fate. What are the prerequisites of such a process? Well, you would have to know the cues that have to be applied to the somatic cells to convert it into a gamete. You would have to know the sequence by which these cues are to be applied. And you would have to know the timing by which these cues are to be applied. And ultimately, as you know, you will have to provide what we refer to as a niche, essentially somatic cells that surround the gamete in the human body, granulosa and theca cells in the ovary, and Sertoli cells in the testes, without which gametogenesis is ineffectual. The beginning was modest. In 2003, a science paper saw press, wherein the lead author was Hans Scholler, who is presently with the Max Planck Institute in Germany, which was titled "Derivation of Oocytes from Mouse Embryonic Stem Cells," an example of which is being shown in the right lower hand side of the slide. That same year, Professor Noche from Japan published on the pages of the Proceedings of the National Academy of Sciences, a similar finding on the production of germ cells in vitro. The same held true for Professor Daly, who is now the Dean of Harvard Medical School, who published a paper in Nature on the derivation of embryonic germ cells and male gametes from embryonic stem cells. And more of the same came from the laboratory of René Rejo-Pera, who at the time was at UCSF and reported on the spontaneous differentiation of germ cells from human embryonic stem cells in vitro. The next 10 years saw a series of influential papers in journals such as Nature, Science, and Cell that dealt with the generation in vitro of germ cells in the rodent paradigm. And much of the same, again, leading journals published on the generation of germ cell in the human. And that brought us to about 2015, at which point the state of the art was that germ cell specification pathway is not conserved between the rodent and the human, meaning they are different. What we learn in the rodent may not always apply in the human. And so that, of course, creates additional barriers for those of us who are interested, of course, in human reproduction. It was also realized that the genetic networks involved are quite distinct as well. And so lessons learned in the rodent are not necessarily immediately applicable to the human. But as you will see, much of the critical early leading work was done by necessity in the rodent. But as we look back at 2015, we can say that we knew how to take embryonic stem cells or induced pluripotent stem cells and convert them to what is known as primordial germ cell-like cells. But we couldn't take it from there all the way to so-called haploid post-meiotic mature gametes. In a word, we understood the extragonadal component of the process, but had yet to figure out the intragonadal component thereof. Final frontier, of course, was in vitro gametogenesis all the way, which at that point had yet to be accomplished. This happened in 2016, finally, courtesy of Professor Katsuhiko Hayashi, who published a paper in Nature titled Reconstitution in Vitro of the Entire Cycle of the Mouse Female Germline. He started with either embryonic stem cells or induced pluripotent stem cells. He combined those cells, or he converted those cells to what is known as pluripotent germ cell-like cells. He combined those with somatic gonadal cells, which you have to have in the context of the niche. That led to the production of primary oocytes, eventually M2 oocytes, which are shown on the left-hand corner of this slide. Those M2 oocytes gave rise to fertilized eggs, a blastocyst, which was implanted, and gave rise to pups. In a sense, in the rodent, that concluded the entire cycle of the female germline, starting with essentially a stem cell, which likely was derived from skin, say, and taking it all the way to pups. It took a while to accomplish the same in the male, and that was accomplished by Professor Mitinori Saito from Kyoto University. who published a paper in Cell Stem Cell titled In Vitro Reconstitution of the Whole Male Germ Cell Development from Mouse Pluripotent Stem Cells. So at that point, it was clear that you could take a skin cell, say, and convert it into a germ cell with all the functionalities thereof, but only in the rodent at that point in time. In human IVG, there are still several missing links. We don't really fully understand the germ cell specification pathway, and we realize that we need an ovarian somatic cell component, but it's not that simple, as you know, to secure granulosa cells or Sertoli cells in particular. But now, as you will see, there are technologies that allow us to do much of the same we're doing with germ cells with somatic cells. In other words, you could take a skin cell and create a granulosa cell, or you could take a skin cell and create a Sertoli cell. And so before too long, we'll be able to possess all the necessary ingredients, or so we assume. The situation, as I alluded to in the human, is still more limited than it is in the rodent. The most advanced paper to date, produced by Professor Saito from Kyoto University, was published in Science in 2018 and was titled Generation of Human Oogonia from Induced Pluripotent Stem Cells in Vitro. He started with primordial germ cell-like cells, combined them with somatic cells. He had to rely on a xenogeneic contribution because we didn't have at the time, let's say, human granulosa cells. And he proceeded to develop these germ cells in vitro, but could only get them as far as the oogonial stage. In other words, we have yet to achieve a point where we develop an M2 oocyte that is, in fact, capable of fertilization. So the missing link in the human is, first of all, the absence of gonadosomatic cells, or the simulation of their input, the so-called niche. But that also is being resolved as we speak. For example, in 2021, Professor Katsuhiko Hayashi reported on the pages of Science a paper titled Generation of Ovarian Follicles from Mouse Pluripotent Stem Cells, doing exactly what we alluded to earlier, namely, take a somatic cell and produce a granulosa cell, or produce a Sertoli cell. And that was accomplished, in this case, in the rodent. Still, we are not in a position to replicate faithfully the entire process of meiosis at this time. And we will have to do that to meet what are referred to as the gold standards, namely, that whatever we produce has the correct nuclear DNA content, the normal chromosome content and organization, the appropriate synapses and recombination capabilities, and the capability to produce a viable euploid offspring. These so-called golden rules were established by Professor Marianne Handel and Professor John Eppig from the Jackson Lab some time ago, but they still hold true. Assuming we get to this so-called promised land, what are the scientific and translational promises that are in store? First of all, we can assume safely that having these cells at hand will advance science. It will provide us with an inexhaustible supply of germ cells. It would allow us to do functional or null-mutant analysis and thereby ask, what is the function of every single gene in the process? We could, for the first time, with some detail, could study germ somatic cell interactions. There would also be clinical implications because we could potentially reverse germ cell failure. We could do this by autologous gamete replacement. We could gene edit gametes that are, for one reason or another, genetically flawed. And we could even use this approach to facilitate the process of mitochondrial replacement therapy. This is a very exciting prospect all around. Just think of patients like patients with Turner syndrome who lack oocytes, but in principle, perhaps could be provided with such if one were to start afresh from a somatic cell. We also need to reflect at this point theoretically on the impact of IVG on IVF. In principle, having these in vitro derived gametes will eliminate the need in stimulation and egg retrieval. This in many ways is one of the more taxing pieces of the IVF process, mostly taxing on women who are given hormones to stimulate the production of eggs and then require the surgical retrieval thereof. That could potentially be a thing of the past if we, in fact, are able to get there. This will also do away with gamete donation, although there could still be the age component, but the whole idea of gamete donation may no longer be entirely relevant. And you could imagine that this would convert IVF, which is an elaborate in vivo procedure today, to a laboratory counterpart. One would still require endometrial preparation, and one would still require embryo transfer, unless we switch to ectogenesis. But that is obviously that's already right there, a great deal of simplification of the current IVF paradigm. Will the simplification improve affordability and thus access is a big question. We always hope it will, but many a times our hopes were dashed. It may or may not come to fruition. And to be sure, we are probably too early to even begin to speculate on this possibility. Now, this cannot happen in a vacuum. You cannot produce eggs and sperm willy-nilly in a lab without regulatory oversight, which almost certainly will have to come under the jurisdiction of the FDA. The branch at the FDA that is concerned with the approval of, in this case, germ cells would be CBER in short, or the Center for Biologics and Evaluation and Research. It's the same center that approves all the COVID vaccines at this time. And in their book, in their classification, germ cells will fall under what they call HCTPs, or human cells, tissues, and products. But this is fairly standard, and there is no question that before this ever comes to clinical use, it will have to be blessed by the FDA. It would also be a good idea, and that's an evolving paradigm that's more developed in Europe than it is in the US, that we as a people engage in public deliberation, or what is known as participatory public engagement. The notion here is that You don't just have scientists go about their craft and do whatever they wish to do without asking the public for its opinion, which is a progressive outlook that has much to recommend. We have really not done this very well, if at all, in the United States, although it's coming. I can tell you that in Europe, not just reproductive issues, but virtually any issue, whether it's taxation or other governmental initiatives, are commonly brought to the attention of the public. And there is a certain formal process by which public deliberation is undertaken. This is increasingly a science, if you will, or at least a model that is evolving in a way that is relatively standard. It is often pointed out that in the United States, not only are we not doing it today, but one example of the lack of public deliberation that is often brought up is the famous 1975 Asilomar Conference on Recombinant DNA, which was well motivated and was wisely convened, but was experts only by invitation and really no representatives of the public. And so, as well-meaning as these scientists clearly were, and they, if you recall, issued a temporary moratorium on recombinant DNA until it was clear that they could proceed safely. But they never checked with the public. And that was not forgotten and not lost on several individuals. For example, the late Senator Edward Kennedy, on May the 9th, 1975, in a speech at the Harvard School of Public Health said, "When science develops techniques that fundamentally change society, society has the right to determine how the technique is to be used, whether it should be developed in the first place, and if so, under what constraints." The National Academy of Medicine issued a report in 1995 titled Society's Choice, subtitled Social and Ethical Decision-Making in Biomedicine, which made a strong plea for the development of public deliberation. In 2008, the National Academy issued another report, in this case dealing with environmental assessment and decision-making, but one which nevertheless called for public participation and deemed it intrinsic to democratic governance. The all-important high priest, if you will, of this field is Professor Sheila Jasanoff from Harvard University, who in her book, Science and Public Reason from 2012, made the point that the issue is no longer whether the public should have a say in technical decisions, but how. And so you can tell that in the backdrop, there is a groundswell of sentiments that supports the notion that the public should have a say. We have published on this issue also back in 2019 in connection with in vitro gametogenesis and argued what we called the public engagement imperative. And we did so with the leaders of the field, namely Dr. Hanna from the Weizmann Institute, Dr. Surani from Cambridge University, and Professor Hayashi from Japan. Just to illustrate the process or the existence thereof, here is an example that dates back to 2021, wherein such public participatory process took place in Belgium relative to the public's attitude towards in vitro gametogenesis. You may recognize some of the participants, such as Heidi Mertes, Guido Pennings, Seppi Seggers, perhaps others, who are well-known names in European reproductive circles, and often are in the United States, of course, for our own meetings and the like. And the meeting, which was titled Reproductive Biomedicine and Society Online, really was a key example of how this ought to be approached if and when we in the United States end up facing up to this possibility. Not quite in vitro gametogenesis, but when it comes to other advanced genetic technologies, the Royal Society in the United Kingdom also conducted what they call a public dialogue and opinion on the evaluation of genetic technologies. In other words, they did a public participatory process that asked the public, what do they think about, for example, germline editing, the notion of manipulating the genome of the embryo. The Nuffield Council, which we mentioned earlier, argued that to do that, of course, you need a body that will lead. And they suggested the establishment of a separate body or commission, independent of government, of course, which would produce an understanding of public interest through promotion of public debate. As we think about it in the United States, we don't really have any precedent or body that can do that, although for the longest of time we had a bioethics commission that was usually put up by the president. For some reason that lapsed in the last two administrations. But we have the Hastings Center, which is our prime center for bioethics. And we can think of other bodies which could potentially take on this task. I will close at this point where we started, namely the notion that in vitro derived gametes are now somewhere in our future. Exactly where, exactly when, only time will tell. But the Nuffield Council infographic was clearly timely in its placing in vitro derived gametes at the top of the list, in that it is at least reasonable to assume that, as I said, the younger members of the audience are likely to be around to see some of this realized in real time. So for now, stay tuned. And if I can be of any assistance with respect to any questions that may follow, I'd be happy to do so. And thank you very much for your attention.
Thank you, Dr. Adachi, for a fascinating, interesting talk. Thank you. You could hear nothing in this room, and everyone was just 110% tuned into your talk. So I want to open this up for question and answers, starting with you all here in the room. Any questions for Dr. Adachi, comments, observations, anything that's on your heart that you want to express?
Hi, Dr. Adachi. Thank you so much. That really was a fascinating lecture.
Thank you.
My question may be way off in left field, but I am just wondering if if you ever foresee a role for cord blood stem cells in the use of like fertility and IVF, potentially, I don't know, this is, like I said, way off in left field, but for a family who lost a child or something like that, that may have banked cord blood.
Yeah, no, thank you for the question. I would say there is no a priori decision made here to use skin cells, for example, although I think I repeatedly refer to them. Really, any somatic cell should serve the purpose. So I don't see any issue with using other types of cells. I was reminded, by the way, and this is mostly for the sake of completion, and some of you may have seen the headlines recently. This, for lack of a better term, gametogenic gymnastics has been taken a step further. And by that I mean Professor Katsuhiko Hayashi, who was mentioned several times, was able to convert, in this case, a male germ cell into a female germ cell, which is a slightly different angle than the one we discussed, but with the implication that a couple of men who live together and wish to start a family could, in principle, at least create an embryo. They would still require a surrogate to carry the pregnancy. But that, of course, is yet another breathtaking feat that was broken 2 weeks ago at the the third meeting of the gene editing conference in London, and since then so press in Nature, and also filled the headlines in all major outlets all over the world. So you can see the story doesn't end necessarily with converting somatic cells into germ cells. Now there is an interconversion, if you will, of germ cells, starting with one particular germ cell and converting it to another, with all kinds of possibilities. Same would eventually be true, if it's feasible, for a couple that is comprised of 2 females. But all of that just points out to what in so many ways, even today, strikes one as science fiction. And yet, it is around the corner.
This is David Ellie. Thank you for that beautiful presentation.
Thank you.
I just, my question is really about public discourse and engaging the public in, it feels, I'd use the word disheartening. And how do you envision in our seemingly bipolar culture, how does one pull this off?
No, good point, needless to say. I think step number 1 in all of these processes is what you might refer to as education or information imparting. You can't expect the public to know what we're talking about. You have to dedicate a certain number of hours, and usually, not usually, but often this is done over a weekend, where you convene 100 or 150 people. You break them up into groups. but you do have to provide them with some information. Now, your reference to the bipolar society, which I completely understand, only means that for those of us who reside in the US, we have to understand and accept that we are hardly homogeneous when it comes to matters of life. This is obviously a uniquely American situation, as you know, in that virtually every other nation around the globe has moved on. It's a very interesting phenomenon as to why we seem to be continuously still preoccupied by the issue, but we are, and we can't ignore that. And so I think that all the more reason, probably, to be sure that we are not dictating or imposing or creating facts in the field without any fair warning or an opportunity to opine. That's the least we must do, especially when you deal with a society that is divided on matters of life.
I think we have a question online.
So we have so far one question, and I saw Dr. May, you had raised your hand. So if you're able to type your question in the Q&A, but Dr. Laura Tapati is on and asked the question, in an environment that is driven often by opinions from the furthest extremes often, can you discuss concerns you see in the US versus other locations with public perception?
Yes, thank you. I can only reiterate what I more or less said in response to Dr. Granger's question. We can't deny that we live in a divided society when it comes to matters of life. And therefore, if you're asking me why we are a divided society on the matters of life, I don't know the answer to that. I did point out that we are almost the last standing nation to be preoccupied by this issue, perhaps with the exception of a few, less and less, South American and Central American nations. But Europe has moved on. Asia never was too preoccupied by this issue. Australia is not preoccupied by the issue. This is a very uniquely American phenomenon which must be recognized and reckoned with. Irrespective of your views or my views, I think it's important that we give an opportunity to a diverse selection of voices to speak as to their feelings about the issue. What ultimately transpires is a different issue, but completely ignoring the diversity of opinion and or avoiding an open conversation on the issues is probably not helpful. I would also, on a more optimistic note, add the following. IVF has not been controversial in the United States. We can spend more time to discuss this statement of mine, but I think it's well supported. And there are some good reasons for that. What we're talking about here is the creation of life, which is important to everybody. I think the debate begins when it comes to the taking of life. And so, as long as you limit it to life creation, which is what IVF is all about, and what in vitro gametogenesis is all about, we might find that this is actually an acceptable proposition, just like IVF is. We have now had IVF for 42 years in the United States. There's not a single law on the books, meaning Congress has not legislated anything against IVF to this day. Those of you who read the recently released book of former Vice President Pence may have noted that he shares the fact that all three of his children were born through IVF. And he goes on to say that IVF deserves the full protection of the law. All of which I think indicates that when it comes to the formation of life, creating a family, there is consensus. That's not where the problem is. And so in vitro gametogenesis, on the whole, I think falls in that general realm and probably will fare well.
Great, thank you, Dr. Adachi. Dr. May with Wichita State University has asked, gametes undergo a developmental process which likely imparts information utilized by the new entity. Are there potential problems in utilization of other cells which do not go through the same developmental process? The impact may become relevant down the road.
Thank you, Jeffrey. It's good to hear from you, if not to see you. It's been a long time. And the question fits the questioner, I should say, as well. Jeff, I don't really know the full answer to this. I think the correct answer is the science that is being conducted here must be thorough, must be careful, must be as complete as possible, which is why I said this cannot be applied willy-nilly. This has to go through significant regulatory oversight by an expert committee on which you might end up serving. And so I couldn't agree more with everything you said. And it's up to, I think, those who, first of all, the scientists who are behind this technology, all of whom, and I know most of them, are very responsible individuals. And of course, the regulatory arm of the government to assure that the last thing we want is to create harm. The whole idea here is to advance family building, not create harm. And so, yes, careful attention to every facet of this will have to be applied, as it often has been applied in the past to other technologies. It'll be wrong and premature to apply this in some willy-nilly fashion in another nation, for example, without having subjected this to really the full regulatory process in all its implications.
Thank you, Dr. Adachi. I believe those are all the questions online right now we have.
This is Lisette Jacobson again. I'm an associate professor with the Population Health Department and also here in OBGYN. And my area of study has primarily been with marginalized populations and health equity. When I personally went through IVF about 25 years ago, the cost was tremendous. We spent our savings. All three of our kids have been born via IVF, and thank God that is how we bless our family. Looking at the work that I do with these populations and knowing there are huge health inequities and health disparities among these marginalized populations. And I'm talking about women of color, low-income women, women who live in geographically difficult areas like remote rural areas. How would you foresee a technology like what is being proposed here to have these individuals have access to this technology and start their families.
No, thank you very much. I definitely appreciate the points you make. And I would say that they're equally applicable to IVF proper, as you, I think, alluded to, except you were fortunate enough to somehow be able to afford it. But as we speak today, this remains a real issue, and I'm referring to straightforward, quote unquote, IVF, because we're obviously nowhere near applying in vitro gametogenesis. But unless you live in a state where a mandate has been enacted by the legislature, which would allow in one fashion or another, to one degree or another, to render IVF more affordable, you are really in a challenging situation unless you happen to be well-to-do in the first place. And whether or not this creates inequity is not a question. It is creating inequities. And it's not a surprise that, for example, in Australia, where the coverage is extensive, 1 in every 20 babies born is born through IVF. In the United States, the ratio is far, far lower. And that is because a large number of individuals who are probably eligible, who probably would require IVF to start a family, are unable to afford it, and no governmental mechanism exists to make it possible for them to proceed. So unless we solve the inequities that clearly exist with respect to IVF as we speak, we will not be solving the inequities that will follow with in vitro gametogenesis, which may transform IVF to a somewhat different procedure. But as I think expressed my skepticism earlier, that may or may not reduce the price tag. In theory, if you move from in vivo to in vitro, you could at least imagine a certain reduction in price. But as I also mentioned, unfortunately, if you take a cynical point of view, we always seem to find a way to jack the price up. And so I can't say that I'm holding my breath that somehow in vitro gametogenesis will change the economy here, or the economic variables that you're referring to. So your point's very well taken. I couldn't identify with it more strongly. But this is still something that our society, and by that I mean American society, but also professional societies, need to keep working on, so that we don't leave people behind. And that doesn't just apply to IVF, as you know, although it's glaring in IVF because it's such a costly procedure. And an elective procedure, quote unquote.
Thank you, Dr. Adachi. I'm trying to get some more.
Good morning again, and for those that are joining us that didn't make the first talk, welcome to our grand rounds here in Wichita OBGYN. Our visiting professor is Dr. Ellie Adachi. Dr. Adachi is here partly sponsored by the department, but also sponsored by a KU speaking award. I did the inviting and Dr. Jacobson did most of the writing for that application for the Bohan Speaking Award. I mentioned earlier that I enjoyed reading the committee's deliberations on this award, which were overwhelmingly positive, which hopefully those people are listening today also. But I won't reiterate all of his credentials, which are extensive. I will add one. Somebody wanted me to tell a story, so I will. So what I didn't mention the first time around that is that Dr. Adachi was an oral board examiner for the American Board of OBGYN and the Division of Reproductive Endocrinology and Infertility. So to be board certified in REI, you have to take the same as general, you have to take a written and an oral exam. So my story is that I didn't have Dr. Adachi as my oral board examiner. I didn't know him well at that point, but after knowing him much better, I'm still glad that I didn't have him as an oral board examiner. I know he would have been very fair. I wasn't terribly excited to walk into the room and see Dr. Rebar, but who also turned out to be a really, really close friend of mine. So that's my story. So we're very happy to have you back, Ellie. And for those that are joining us from Kansas City and hopefully Salina and Wichita State, we're excited to hear the second talk, which is entitled Remedial Germline Editing Prospects and Possibilities. It's all yours.
Thank you, David. I assume you can hear me well. You'll let me know if there's an issue, right?
Yes, we can hear you well.
Okay. Well, thank you yet again for the kind introduction, let alone for the invitation. As I mentioned earlier, there was a time when I would visit Wichita far more frequently, but that goes back to the 80s and the 90s. I really didn't have the opportunity to do so now for probably a decade. And when you throw in the recent COVID pandemic, that just makes really anything far more complicated than it should be. But hopefully, somewhere down the line, we can work something out that would allow us to reconnect in person, face to face, rather than via Zoom. The topic that Dr. Granger just reiterated, by definition, is also a futuristic topic in the sense that it is definitely not operational at this time. And yet, we can all see the value of it in principle once we can assure ourselves that it can be applied safely and effectively, which is the same thing we just said when discussing in vitro gametogenesis. This is obviously a slightly different angle, but in a final analysis, both presentations today are about what is possible, not necessarily what is already operational. What is possible and what would it take to put our mind at ease that this technology can be put to good use and safely so. And the same issues obviously apply to in vitro gametogenesis. It's more of the same in that respect, but really a very different technology, different set of circumstances, but a future that, as I suggested earlier, is likely to be witnessed by the younger members of the audience, because it's going to take a while to actually get this one to a point where we are all comfortable with it. I should say perhaps at the outset that the search for genome editors has been underway for some time, really beginning in the 80s. And I should say that even though we have CRISPR today, and I'll say more, of course, about that, the search is ongoing. I wouldn't be surprised if some novel gene editing capability emerges. The first set of genome editors that caught our collective attention were the so-called meganucleases. They were unwieldy, they were imprecise, and always left us with the sense that we better improve on the state of affairs, which led in time to the so-called zinc finger nucleases, which was somewhat of an improvement, but still we could all tell was unlikely to prove to be the state of the art. The next generation of genome editors were referred to in short as TALENs, or transcription activator-like effector nucleases, which once again introduced certain benefits and advances that didn't exist in the predecessor generation, but were hardly perfect in terms of what one can do and how safely one could do it. Which brings us to the latest iteration in this sequence, and that is of CRISPR-Cas9 and its congeners, because there's a whole slew of family and derivatives, some of which we will allude to, that are being created and applied to good use, and really are making a difference that one fine day will actually be clinically relevant. We sometimes forget that CRISPR has only been with us for a decade, maybe 11 years if you want to stretch it. But it's a recent arrival, first reported on the pages of Science in 2012. The leading authors, as you probably know, being Jennifer Doudna and Emmanuel Charpentier, who were the senior investigators who collaborated on this project, and who, as a result, received the Nobel Prize in physiology and medicine in 2020. Clearly, this was a major breakthrough in the sense that it afforded us with a tool, the capabilities of which far exceeded all that was feasible beforehand, which is precisely why the Nobel Committee could see the significance of this breakthrough and why the Nobel Committee awarded the 2020 Nobel Prize to these two investigators. What stands out about the CRISPR-Cas9 endonuclease, a three-dimensional depiction of which is attempted here, is its targetability. In other words, you can choose more or less, although it's imperfect, the sequence you wish to modify. You can do so with relatively high fidelity and with significant malleability and remarkable versatility, which is not to say that CRISPR is perfect, as we will see in just a moment, But compared with the predecessors I described, it represented a sea change, which is exactly why it received so much attention in the last decade. I think if any of us ventured to look in PubMed and attempted to count the number of papers that use CRISPR, make mention of CRISPR, of course, the number will be astronomical. Now, what CRISPR does, among other things, is perform double-strand break-dependent editing, or DSB-dependent editing, which means that in principle, it could repair a multi-base mutation. Now, this is sometimes referred to as homology-directed repair, or HDR. However, this is hardly perfect, because when you embark on editing with CRISPR or other agents, it triggers a non-HDR DNA repair mechanism, which the cell activates from its point of view as a defensive mechanism, which gives rise to so-called non-homology end joining, which is immediately translated a distortion of the architecture as it once existed. This could amount to small stochastic on and off target insertions or deletions known as indels. So essentially mutations in the sequence, or worse, large on-target deletions and complex rearrangements, including, as we will see later, the outright loss of whole chromosomes. And so, powerful as this technology definitely is, unless we are able to provide it with tools that would limit, if you will, or circumscribe its activity to the desired effect, we are going to be struggling with circumstances that are incompatible with clinical safety. Later on, probably about 5 years ago, the notion of double-strand break independent editing emerged. The notion of base editors, or the ability to repair a single base mutation rather than a sequence of mutations, or a string of bases that are off the mark. This is the contribution of Professor Liu, primarily from the Broad Institute, who I think is correctly viewed as the father of base editors. And those base editors can carry out much more refined and self-limited tasks, such as converting a CG pair to a TA counterpart, or an AT pair to a GC counterpart. And base editors have now been developed and redeveloped and modified in a variety of ways that extend their utility in a significant fashion. Perhaps not enough yet to put all of us at clinical ease, but clearly indicating a forward movement and a degree of progress by exceptionally capable scientists who sooner or later, I think, will provide us with the right kind of tools for the task at hand. This could be summarized as follows in terms of the CRISPR challenges. It's not always as efficient as you would like it to be. I've already dwelt on the fact that it's still a long way from achieving the kind of specificity we will require if we are going to apply it to living people. And it's also lacking in the uniformity of its action, giving rise not that infrequently to unpredictable consequences that we cannot tolerate from the point of view of clinical safety. Nevertheless, this is a very valid concept, a valuable one, a lofty one that we should strive to perfect. And the reason for doing so, or the objective of doing so, is really to prevent disabling and life-truncating, primarily monogenic maladies, because on the surface at least, these are the simplest to correct. And I put simplest in quotes because, as I already indicated, nothing is really simple in this arena. But maladies that are contingent on a monogenic aberration lend themselves probably the best to this technology, or lend themselves first to this technology. And this has been referred to by some as remedial germline editing, because remedial for all the obvious reasons, germline because it would be applied either to a gamete or to an embryo. And in so doing, will apply to presumably all the cells of the resultant human being. So if the correction is done at the germline stage, in principle, we can create a life that is free of genetic disease if we know what is wrong in the first place, and if we have the technology to safely go about reversing it. You could say that what this is all about is converting from chance to choice, rather than passively observe whether or not a particular malady is inherited and expresses itself in the offspring. We can make a choice and hopefully control what the outcome in principle would be. And yes, one would have to say that this is a lofty goal, but I would argue a worthy one, that in theory, and I emphasize at this point in theory, could rid humanity of the so-called monogenic scourge. Now, those of you who are either in the business of perinathology or are genetic counselors or in any way involved with screening for genetic pathology, recognize that the universe of so-called monogenic diseases is substantial. The OMIM, or Online Mendelian Inheritance in Man database, lists over 10,000 human monogenic disorders. And so there is no dearth of pathology that could be addressed, even if one limits oneself to the monogenic paradigm. Edit-suitable maladies, I would say in general, are those that right now are such that peri or postnatal medical therapy is infeasible. We cannot apply a medication, if you will, to address the problem once it occurred. Or at least we have limits imposed on our ability to bring the individual in question back to its healthy, steady state. The other issue is that these technically correctable maladies are such that they cannot be corrected after an individual is born, or not as well, because that would require somatic editing of all the cells in the body. And as we know, that is not very practical, and at this point, definitely undoable. The only somatic editing that is currently being done or seems to have some promise is one that involves the bone marrow. For example, sickle cell disease, where one can hopefully remove some cells from the bone marrow, edit them appropriately so as to correct the underlying deficiency, and then re-inject those cells into the body. And that is being attempted, I should say, as we speak. But as a whole, if the pathology is in the liver, in the lung, in every cell in the body, somatic editing will not do the job. You really have to deal with the situation in the single cell stage, which is to say, at the stage of the embryo. Editing will also be helpful in situations where PGD is, for one reason or another, inutile. That doesn't happen very often, but there are circumstances wherein PGD is not going to provide the answer. And PGD, not unusually, might give rise to a rate-limited embryo complement, which again, one would like to work against. Ideally, the target allele would be highly penetrant, singular, and most importantly, CRISPR accessible. So these are some of the, shall we say, preconditions that would favor germline editing if and when it becomes feasible and, most importantly, safe. Which brings us to the all-important question of what is the state of the art as we speak today. And I plan to more or less spend the rest of the time to take you through the history of germline editing, if you will, to the very recent past, and point out what you probably surmised already, that we're not there yet. We're working hard towards that end, but the technology is simply not good enough to be safe enough. And that's why I refer to the state of the art as nascent, because that's probably the most complimentary description we can provide to state where we are today. For the optimists among us, this could be rephrased to read, so near and yet so far. It really seems within grasp, but in reality, it's still quite a way away. I don't know. I don't want to say a long way away because we don't really know, but it's definitely not here today. You could say that the first effort at human germline editing, and I don't mean by that human in the sense of an embryo that was going to be implanted, as you will see, but an effort to at least begin to address the editing of embryos was undertaken in 2015 and was published on the pages of Protein Cell. The paper was titled CRISPR-Cas9 mediated gene editing in human tripronuclear zygotes. Wisely, the investigators did not use viable zygotes or embryos to work with, but rather tripronuclear zygotes that would never be transferred. The investigator in question was Professor Zhongju Huang from Sun Yat-sen University in China, who reported a gallant effort at, in this case, addressing a malady in the beta globin gene, but he honestly reported low editing efficiency, minimal editing specificity, and limited editing uniformity. In a word, it was very clear at that time, using embryos that were never to be transferred, that the technology is barely getting underway, and that at that point in time, definitely, the precision left a huge amount to be desired. Nevertheless, probably because it was a first, Nature chose to include this paper in its so-called Nature's 10, or the 10 people who mattered this year. And they do dedicate a small paragraph, as you can see here, to what they describe as the embryo editor. And they did so because of the importance of the concept, definitely not because of the results that were achieved. About 2 years later, in February of 2017, the National Academy of Medicine released a committee report, and you need to realize that those take months, sometimes years, to produce, and multiple meetings of a committee of scientists who meet at regular intervals, usually in DC, who bring in various visitors and who testify on this or that matter, experts who are being summoned to inform the committee. So it's a long process, but at the end of which a fairly thick report is published, could be 200, 300 pages long. In this case, the report dwelt on the science, the ethics, and the governance of human genome editing. It didn't specifically dedicate itself to germline editing, but it did put some emphasis on this issue. And as you can see from the statement that I will not read on the right-hand side, they too were at the point where one could definitely make the point that germline editing is promising, but it's yet to really be perfected, not to mention to be stringently overseen, as they suggest here, and subject to very specified criteria. On August of that same year, A paper saw press in Nature titled Correction of a Pathogenic Gene Mutation in Human Embryo. And that paper was senior authored by Professor Shukrat Mitalipov from the Oregon Health and Science University. What Professor Mitalipov sought to accomplish is to correct an autosomal dominant malady attributable to the sarcomere gene MIBPC3, which gives rise to familial hypertrophic cardiomyopathy. As many of you may remember, although this may go back to medical school for some of you, this is an incurable condition. It is at the best amenable to symptomatic care, and more often than not, sadly, ends up with sudden cardiac death. Definitely a worthy target of intervention if one could, in fact, achieve such. Dr. Mitalipov undertook 2 sets of experiments. By that I mean he elected to edit the embryo at 2 different stages. The first was the S phase, or 18 hours post-fertilization. And in the zygotes that he edited, he reported editing efficiency of 67%, that is to say, resumption of wild-type homozygosity, but a mosaicism rate of 24%, and some on-target indels. He then took a different approach, and edited the embryo in the M2 phase. So he edited zygotes essentially at the time of fertilization. At this point, editing efficiency was 72%, and the mosaicism rate was far lower, now down to 2.4%. In both cases, as I mentioned, there were on-target indels. Nevertheless, viewed optimistically, this was a marked improvement. And Dr. Mitalipov concluded that zygotic editing at fertilization, the second paradigm, enhances editing efficiency and uniformity, if not specificity, but that further optimization will be required if clinical application is to be entertained. Somewhat surprisingly, but eventually convincingly, post-publication, this paper was heavily criticized on the pages of Nature on August 9th, 2018, by several respectable scientists who work in this area, who asked the question, does the interhomolog repair presumption hold up in the paper? Have CRISPR-mediated rearrangements, large deletions, and loss of heterozygosity been missed? In other words, could Dr. Mitalipov have missed, for example, the loss or the outright loss of a whole chromosome, which I will show you later is a real possibility? And has the hoped for wild-type homozygosity been unequivocally documented? Again, questioning the result and documenting why in a series of papers that went back and forth on the pages of Nature in the wake of the application. Clearly not something anybody would like to see, because one would hope that whatever papers are being submitted, especially, but not just, to a journal such as Nature, are vetted to a degree that leaves little room for guessing or questioning. But this was not the case. Several serious investigators questioned the conclusions of the paper, which obviously left all of us feeling that the progress we thought we made, we may not have made, and that the conclusions drawn by Professor Mitalipov initially may, in hindsight, have been overstated. Partly as a result of this, partly as a result of other studies, some of which I will share with you, the National Academy of Medicine and the Royal Society of the United Kingdom formed a joint committee to evaluate heritable genome editing yet again, and to issue a consensus study report. The meeting was, or the committee was co-chaired by Kay Davis from the UK and by Richard Lifton, who is the president of Rockefeller University from the United States. The committee issued a conventional consensus study report, the concluding summary of which I provide here. The key, and shall we say relevant, conclusions that I'm showing here included one that stated that no attempt should be made to, quote, establish a pregnancy in a human embryo that has undergone genome editing. This is, of course, a very strong and unambiguous statement, and it makes it plain that the science is simply not yet where it needs to be to accomplish what we all think is a worthy cause, but only if done safely and predictably. The committee further recommended that the clinical use of heritable human genome editing should proceed incrementally. You might say that that's a commonsensical, predictable recommendation, but the committee was clearly of one mind that the time has not yet come and that some incremental, careful work needs to be done before this technology can be deemed safe and effective. The committee also recommended that clinical use of heritable human genome editing should be limited to serious monogenic diseases. In other words, if you're going to do it, start with the serious monogenic diseases. We could argue with this recommendation, and some have, but this is the recommendation that the committee made. I think had I been sitting in that room, I may have had something to say about it, but they still mean well and are advocating caution. And finally, points 5 and 6 of the report was that clinical use of heritable human genome editing must guarantee impeccable editing efficiency, specificity, and uniformity, as well as euploidy and appropriate embryonic developments. In a word, it must not interfere with the normal developmental process. It only should do what it's supposed to do in a surgical, highly accurate, precise fashion, and let all the rest proceed as usual. Easier said than done, but perhaps it needed to be said. That same year, as if to affirm some of the committee's recommendations, a paper from the laboratory group of Professor Egli from Columbia University, New York, saw press on the pages of Cell, the title of which was Allele-Specific Chromosome Removal After Cas9 Cleavage in Human Embryos. And when you read the in-brief summary on the front page, it reads, CRISPR-Cas9 gene editing in early human embryo leads to frequent loss of the targeted chromosome, indicating that human germline gene editing would pose a substantial risk for aneuploidy. In other words, it will generate aneuploidy and other adverse genetic consequences. Looking at this paper in a retrospective fashion, this is perhaps one of the reasons that Professor Mitalipov's paper was questioned as to whether or not it simply missed the loss of chromosomal material in the original paper. He goes on to explicate, as shown in this statement about chromosome loss, and hastens to add that off-target effects of Cas9 cause inserts, deletions, and chromosome loss. Clearly, a significant indictment of the technology as it currently stands. And as you will see in a second, he's not alone in documenting such. And so if we come away with any conclusions from this conversation, it is really what we started with. This is a worthy technology. It's a worthy cause. It's just not ready for prime time. And until such time that it is ready for prime time, it ought to be confined to the laboratory. Further affirmation of much of what we already said was provided on April the 9th of 2021 in a paper that was published on the pages of the Proceedings of the National Academy of Sciences, the senior author of which was Kathy Nayakan, who is an American investigator, but who presently lives and works in London. And in essence, what Professor Nayakan and her group stated is that further basic research is required to assess the safety of genome editing technique in human embryos. Very clearly placing the technology under the microscope. And I will not go into greater details, but her findings were largely affirmative of those of Professor Egli. So in summary, embryo-based, clinically reliable heritable human genome editing appears to be unlikely in the foreseeable future, and that's important to realize. Gamete-based heritable human genome editing using cultured stem cell-derived eggs, which we discussed, or sperm, may well prove the preferred route forward if, and only if, we can document that at that level, we can more safely or entirely safely and effectively achieve the goals we are aspiring to. And so I'll conclude by saying, stay tuned, because this story is nowhere near conclusion. And I would place it behind in vitro gametogenesis in terms of its state of development. Now, of course, in vitro gametogenesis has been underway since 2009. And heritable human genome editing, as you can see, in a serious fashion really hasn't begun until 2017. And after all, CRISPR is only 10 years old. So this field is lagging, you might say, behind in vitro gametogenesis, which has a large number of investigators involved who have been diligently working on this since 2009. Parenthetically, I will say that I was excited by the prospect of in vitro gametogenesis as soon as it became apparent. And in 2013, I was in Japan, and I made a point of booking a flight to Kyoto strictly so that I could meet in person with Michinori Saito and Hatsuhiko Hayashi, who were then working together in Kyoto, and to hear firsthand from them where in vitro gametogenesis was going. In the 10 years since, as you have seen today, it's come a long way. It's not quite there yet, but it's far closer to the finish line than is heritable human genome editing. Now, of course, they had a head start, and it's a very different technology, and you cannot really contrast and compare. But viewed globally, these are two technologies that at one point or another, I suspect, will permeate, in some respect, dominate our discipline, and in so doing, will change lives that up until now could not be helped. And it is for these reasons that I'm so intrigued by these technologies, even though they may not be ready for prime time. But I can see the promise. I'm sure you can too. And at one point or another, hopefully we, the collective we, will be satisfied that these technologies are safe and effective, and therefore can be applied to enhance really human flourishing. So with that, I will stop. There's obviously more to say, and there are even more slides, but I think this summarizes probably most of what I wanted to convey to you. And I hope that I was successful in doing so. So thank you very much for the opportunity to share this morning with you, to share these two futuristic topics with you, in the hope that I've been of some service. So thank you very much.
Thank you, Dr. Adachi. Another fascinating talk. Questions, Q&A. Now's the time to ask your questions. We may have some online. Jennifer will monitor online chat. Dr. Green.
Thank you, Ellie. It's David. So I have a couple of questions. The first one, you mentioned that one of the committee recommendations was that germline editing be only applied to severe monogenic disorders. And you said, had you been in the room, I'm just curious what your observations or arguments might have been at that point?
Well, it just struck me as a little bit premature. If the technology is unworkable, it's unworkable for any type of condition. I mean, I understand where the committee came from and why they wanted to emphasize conditions that are potentially addressable. But I thought there was, it wasn't a cardinal sin, but I thought it was a bridge too far. I would have probably crafted it differently. That's not to say that I bear any disrespect to the committee or its conclusions, but let's just say that we are all entitled to our opinions and we respond to what we read perhaps in a differential fashion.
Understood. My second question, I just wondered if you could maybe enlighten us on what was a very newsworthy event in China regarding the use of germline editing.
No, that's a good point. I debated whether or not to include that here, but because of the all around unfortunate circumstances, I didn't see it as constructive in any way, other therefore reminding us all that you cannot do science willy-nilly in a manner that cannot be condoned. But what Dr. Granger is referring to is the work of a certain Dr. He from China, which was not reported to my knowledge in the scientific literature, but was reported in the first genome editing meeting, which is we are now at the third genome editing meeting, which just took place in London. But the first, or maybe it was the second genome editing meeting, which took place in Hong Kong. The first one took place in Washington, D.C. And in that meeting, Dr. He reported verbally from the podium on experiments that he has done involving 2 future girls in whom he ostensibly sought to modify the CCR5 gene, and in so doing, provide them with protection against HIV. Now, there are so many points here that deserve mention. I'll just limit myself to a few. First of all, this was done willy-nilly without the approval of a committee, without appropriate consent forms, not to mention without solid scientific foundation, in that it's still debatable to what degree CCR5 provides protection against HIV. And it's far from clear that the technology used, which was never reported, produced the desired results. In fact, we can safely assume from the work of Dr. Egli, Nayakan, and others that Dr. He, unknowingly probably, produced all kinds of damage that will come back to haunt us in those 2 girls who were eventually born. As you know, he was sentenced, tried, and sent to prison for, I think, a period of 3 years. He has recently emerged from prison, and occasionally you hear some statements or utterances from him I'm not really sure what the future holds for him. But what he did was deplorable, in no way warranted, and is widely used as an example of a scientist gone rogue, a scientist who simply did not abide by the rules, as a result of which we now have two girls whose future is somewhat uncertain. We may or may not know anything now. I'm not sure we will know much anytime soon, but none of us would have wanted our children to be subjected to a technology that's never been used, never been validated, and in hindsight, as we have seen, can be exceptionally disruptive. So this is more or less an abbreviated version of the story of Dr. Hay, about which a book has been written and much has been said and is still being said, but in no way is any of that commentary positive, or it's only commentary to denounce what was really a deplorable incident.
Thank you. And it does sort of re-emphasize the need for regulation and oversight that you've made so clear today.
Hi. I just wanted to ask, this is sort of a piggyback off of the last question, but it's easy to give recommendations and regulate on the proper use of this technology, such as limiting the application of monogenic diseases and proceeding safely and incrementally, all of which could lead to significant public good in curing diseases. But I think it's also worthy to discuss the theoretical application, even though it still may be years away, but could have huge potential implications on society. I mean, developing the technology to cure diseases is also developing the technology to edit other genes as well. And some people will use the technology following the rules and others will not. So I was just wanted to ask you what you think the implications are for opening Pandora's box, so to say.
Yes. No, I fully agree with the tenor of your question. I obviously have no qualms about the good that could come out of this technology, and I hope I made some of that clear when we talked about the 10,000 monogenic disorders, but there are obviously non-monogenic disorders as well. And we mentioned briefly the recent efforts to do a little bit of at least non-germline therapy, but rather somatic gene therapy. But I think dwelling on possibilities and identifying targets is definitely a worthy undertaking. I might add in parentheses that this whole field led me to a whole new long-term project that we're in the midst of, and the combination of which is still unclear. But if you're at all a geneticist or related to a geneticist or working with geneticists, you probably realize that the OMIM database, which is ancient in some ways, is really not workable, is not helpful. And we need better tools, in other words. And so with a group of other individuals, some of whom are experts in the necessary computational technology and geneticists and others, we have embarked on what is really a long-term project to redo the OMIM database. In other words, use the same data, but render access to them more user-friendly, more dependable. So I mention this only because picking targets, we can definitely pick many targets, but there are some limitations that we recognized when we learned about the limitations of the OMIM database. And anybody who works with the OMIM database will tell you that there's much room for improvement. Whether or not we will succeed, whether or not we'll even conclude the project, time will tell. But we are in the midst of trying to do some good there, which would help along the lines that I think you brought to our attention.
Yes, so Dr. Adachi, there is a question online from one of our residents, Dr.
Okay.
Jordan Longabaugh. How, if so, has CRISPR improved since it was introduced in 2012? And do you feel that we are moving closer to goals of uniformity and efficiency with the technology?
Well, thank you for the question. And the eternal optimist that I am, and I think that's not an unreasonable proposition here. CRISPR, which we mentioned is now 10 years old or 11 years old, is barely in its infancy. And yes, there are thousands of papers that deal with CRISPR, but it probably will be some time before we can extract from CRISPR the value that I think we all expect it will yield. And every day when you open the journals, Nature, Science, and others, you will probably run into some modification of the technology that is intended to improve it. For example, the base editors that I mentioned were really a remarkable improvement on what we had. It didn't solve all the problems. It has its own issues, but the world is replete with creative scientists. And sooner or later, there's no doubt in my mind, these bugs are going to be ironed out one way or the other. I don't know when, I don't know how, but I have strong conviction that it's just a matter of time. Of course, when we say CRISPR, we also need to realize that it's no longer a single species. There are all kinds of CRISPRs now, and more will probably be found. And it's entirely possible that that itself will create advantages that were not inherent in the original variety. So any way you look at this is now a huge field with probably, I'm not exaggerating, I assume thousands and thousands of scientists being involved in one way or another all around the world in basic science, clinical science. I have no doubt that this collective effort, sooner or later, will yield the kind of breakthroughs that will make it possible for us to embark safely someday on gene editing, whether somatic or germline. Germline simply has more possibilities in many ways. Somatic will require additional technology to be developed that will allow one to develop CRISPR or a congener in a tissue-specific fashion. I mean, how do you treat a liver disease in an adult? You have to somehow find a way, ideally at least, to target the editing to the liver only, if you can help it. And the liver may, in fact, be more accessible than some other tissues. How will you address, let's say, a lung pathology? A single cell, an embryo, that derives from parents who already have a history of genetic disease and who want to prevent the transmission of that disease to their child, and in so doing, prevent the transmission of this disease to all the subsequent generations down the line, opens up, I think, in many ways, greater possibilities. And that's not to diminish the suffering of people who are already in the adult stage and whom we would like to lend a hand. But it may be trickier, more challenging, more time-consuming, which is why I think germline editing at least has the potential of being achieved, and you'll have to define it for yourself, a reasonable period of time, whatever that means. We don't need to figure out a way how to deliver reagents to the embryo or to the gamete. They're in a dish, and you can deal with them in a very different fashion than you deal with, let's say, a lung in vivo, in a living, breathing individual. So much to be said for germline editing, but also a long way to go, it seems.
Looks like that was the only question online for right now.
Any other questions from the room, audience? Well, the session is being recorded. So, so we'll go ahead and make sure that the recording will be available. So, if you have questions after you maybe review the lectures, we may be able to contact Dr. Adachi with those
Sure.
questions. Good, good. Thank you so much, Dr. Adachi, for sharing your knowledge, your wealth of knowledge with the audience in this room, the audience online in Kansas City and in Saline. And we thank you from the bottom of our heart. We will be in touch really soon. I know Jennifer, logistics wise, will work out a few more details. Are there one more time, any other questions for Dr. Adachi from the room?